Welcome back to the AI Research Roundup. I am your host, Alex. Today, we're looking at a trending paper called Advanced Long-Term Earth System Forecasting by Learning the Small-Scale Nature. The core problem it tackles is that AI models for climate prediction often become unstable over long simulations. This is because of a problem called spectral bias, where models are good at learning big patterns, but fail to capture small-scale, high-frequency details. So the researchers propose a framework called Triton, which uses a hierarchical architecture, meaning it processes information at multiple resolutions simultaneously to explicitly model those small details and prevent errors from accumulating. And for those of you who want to dive in and experiment yourselves, the authors have made their work fully open source. They released the official PyTorch implementation on GitHub. It seems really well put together with all the key experiments, like global weather forecasting and ocean simulation, organized into their own folders along with all the necessary training scripts. Alright, and this first figure from the paper really gives a fantastic visual summary of what the researchers accomplished. Across the top, we see several examples of Triton's long-term forecasting. The first panel is particularly impressive. It shows a full one-year forecast of global mean temperature. The model's prediction almost perfectly tracks the real-world data, and it does this auto-regressively, meaning it's running entirely on its own without any corrections. The plots below this graph confirm the model successfully keeps errors in check, especially for those small-scale details we talked about. The next few panels show its performance in other challenging areas, like accurately forecasting complex ocean eddies for 120 days, and simulating turbulence while preserving the fine, swirling structures that other models tend to blur out. So how does it do this? That's what the bottom of the figure illustrates. It shows the core architecture, a multi-grid V-cycle. The process starts with high-resolution input, then follows a restriction path, which downsamples the data to capture large-scale dynamics. Then, a prolongation path builds the high-resolution prediction back up, reintegrating details using what are called skip connections from the first path. Alright, so with that V-cycle architecture in mind, this next figure drills down into the competitive performance. Panel A again shows that one-year temperature forecast, but now you can see how the Pengu model completely breaks down after a few months, while Triton stays on track. Panel B shows a 210-day forecast for T850, which is temperature at a specific altitude, and Triton's map looks very close to the ground truth, unlike the others. The bottom plots really quantify this, showing the root mean square error, a common way to measure a model's average error. For multiple ocean variables, Triton's error, the solid line, stays consistently lower over 120 days. So, building on that ocean forecasting performance, this figure zooms into a really tough test case, the Kuroshio region, famous for its complex ocean eddies. The maps show a 40-day forecast where Triton preserves these fine, swirling structures, while a competing model just blurs them out. The energy spectrum plot explains why. This shows energy across different scales, and Triton's prediction follows the ground truth perfectly, especially at high wave numbers, which represent those small details. This translates to better long-term accuracy, as shown in the final plots. They use the anomaly correlation coefficient, a metric for pattern similarity, where Triton's score stays incredibly high, near 0.9, for over 100 days. And this ability to handle complex fluid dynamics isn't just for oceans. This figure shows Triton forecasting 2D turbulence, a classic physics challenge. The top images track the vorticity field, which is the local spinning motion in a fluid. Triton's forecast stays incredibly sharp, preserving these fine vortical structures, while other models quickly blur out. The graphs below quantify this. Triton's average error stays significantly lower over time. And just like with the eddies, its energy spectrum is spot on. It correctly reproduces the theoretical K to the negative 5/3 scaling law, which is a key signature of realistic turbulence. The final plots show error over time, and you can see that for other models, error rapidly explodes in the high frequencies, which are those small details Triton handles so well. So we've seen these incredible year-long weather forecasts, and this table gives us a look at the data that makes it all possible. The model was trained on the ERA5 reanalysis dataset, which is a massive collection of historical weather data. And as you can see, Triton learned from 69 different atmospheric variables. This includes things like temperature, humidity, and wind speed, not just at the surface, but at 13 different atmospheric layers as well. This comprehensive dataset, covering a wide range of conditions from the ground up, is what allows the model to learn the complex, multi-scale physics we saw it capture so well. Alright, and just as that broad weather data was key for the global forecasts, this next table shows the specific data set behind those amazing Kuroshio eddy predictions we saw earlier. This data comes from the Copernicus Marine Environment Monitoring Service, or CMEMS. It provides daily measurements of geostrophic velocity, which is basically the large-scale ocean current, from 1993 all the way to 2024. The table shows it breaks this down into zonal, or east-west, and meridional, or north-south, components. This long-term, high-resolution data is exactly what Triton needed to learn the complex, multi-month life cycle of those eddies. From global weather to specific ocean currents, it's clear that Triton's success comes from its ability to learn and preserve those crucial small-scale details that other models often miss. This work represents a huge leap forward in long-term Earth system forecasting, showing that deep learning can capture the fundamental physics needed for more accurate, reliable predictions. It's truly exciting stuff. Well, that's all the time we have for this week's AI Research Roundup. Thanks for tuning in, and I'll see you next time. I'm your host, Alex.